When engineers design digital circuits by hand, the math piles up fast. Pages fill with intersecting lines and crossed-out variables as they simplify logic equations. This traditional method relies on Boolean algebra. Boolean algebra is a branch of mathematics that deals with variables that are either true or false, using complex theorems to reduce formulas to their bare minimum. Humans easily make mistakes when tracking these variables. Dropping a single prime or misplacing a parenthesis on step 2 infects the rest of the calculation, ruining hours of work. This diagram shows a 5-variable truth table. It contains 32 distinct rows of zeros and ones, representing every possible state the circuit can exist in. Tracking this much data simultaneously pushes the limits of human working memory. Relying on paper and pencil to sort through these states creates a computational bottleneck that slows down the entire hardware design process. Those abstract zeros and ones directly determine how a physical circuit board is built. Engineers frame these circuits using 2 primary methods: sum of products, SOP, and product of sums, POS. SOP logic targets active true outputs, using AND gates feeding into OR gates, while POS logic focuses on false outputs to build the circuit. If an equation isn't perfectly minimized, the extra variables dictate the installation of redundant logic gates. These unnecessary physical components draw extra power and generate excess heat. Leaving even one extra variable in the math guarantees a final piece of hardware that is bloated and inefficient. That mathematical chaos disappears when mapped out visually. Prime ToolHub's advanced K-map solver takes up to 5 variables and automates the entire process, replacing pages of algebra with interactive geometry. This visual representation shows a 4-variable K-map grid. The solver takes the vertical data load from a truth table and folds it into this flat, readable 2D matrix where patterns become obvious. To eliminate variables, the tool groups the active cells. Following the power of 2 rule, the solver automatically circles adjacent cells in sets of 2, 4, or 8 to isolate redundancies. Wraparound logic allows the solver to treat the grid like a continuous cylinder. By connecting the far left edge directly to the far right edge, it identifies large simplified groups that are invisible on a flat plane. The system also factors in don't care conditions. These are theoretical inputs that will never occur in the real world. By marking them with an X, the solver can artificially expand its group sizes to cut out even more variables. Visual K-map grouping turns a dense logic problem into a recognizable geometry problem. Beneath the colorful interface, the engine runs a highly optimized variant of the Quine-McCluskey algorithm. The Quine-McCluskey method is a complex tabular algorithm used to systematically find all the prime implicants in a Boolean expression. Unlike most advanced calculators, this solver executes those heavy algorithms entirely offline, directly within your local web browser. Running locally means the computations happen instantly, without waiting for a server to respond. Your proprietary circuit designs never leave your machine, ensuring complete data privacy. Real hardware optimization requires heavy computational muscle, operating in a secure, frictionless environment. Once the solver maps the grid, it immediately generates the data needed to build the actual hardware. This split-screen diagram shows how the visual groupings on top directly construct the finalized Boolean equation below. Every color-coded loop translates into a clean, minimal string of logic. The system then takes that logic and exports it as synthesizable Verilog HDL code. Verilog is a hardware description language used to model electronic systems. Generating it automatically allows engineers to bypass manual coding. This process automates the foundational programming architecture required for modern digital design, instantly producing functional code from raw logic. That code translates directly into physical pathways, where electrical energy pulses flawlessly through unhindered parallel tracks on the board. The exported Verilog is immediately ready for deployment into high-end workflows for FPGAs, which are programmable logic chips, or into ASICs, which are custom integrated circuits tailored for a specific task. Prime ToolHub provides this automated pipeline completely free without requiring any user registration, saving engineers hours of tedious manual labor. Mastering digital circuit architecture means abandoning the scratchpad for intelligent visual automation at Prime ToolHub.